Hello, Professor Gertner. This is a demonstration of a single-cycle CPU with a read-only instruction memory. Memory comes pre-programmed with 9 instructions, enough to perform a small loop which adds all the integers between 10 and 1 inclusive. The final result of this sum should be 55 in decimal, which is 37 in hexadecimal. My board is set up like so. These first 5 switches I can use to directly inspect the instruction memory. Then switch 15 over here allows me to switch between having the program counter address my instruction memory or these switches address my instruction memory. Switch 16 toggles between showing CPU state information or reading directly from the instruction memory. So this is the first instruction that my program would execute. Right now we're going back to what's normal. And then this last switch, switch 17, allows me to toggle between seeing the program counter and seeing the last output from the ALU of my processor, with the switch being up being the program counter and the switch being down being the ALU output. So right now, program counter is 0. It's pointing to the very, very first instruction in my instruction memory. And I use these push buttons to control the CPU as well, this being the manual clock of my CPU, and this clears the program counter of my CPU, which also allows me to restart this program anytime I wish. So this is the actual program that's going to be run on my single-cycle CPU. On the left here, you can see the actual address of each instruction in my instruction memory. On the right, you can see the machine code of each instruction, which is in my instruction scheme for my CPU. I had to handwrite these myself. And on the right, you can see an assembly-like form of each instructions, what it would look like as if there was an assembly language written for my processor. This is just for explanation purposes for humans. So the first thing it does is it sets register 0 to 10, first by clearing it to 0, then adding 10 to that. Then it zeroes out register 1. Then it sets register 2 to 1. And we're going to use this for comparison purposes, for stopping the loop. This is the actual loop. First thing it does is it adds register 0 to register 1 and stores the result in register 1. So it just accumulates the values between 10 and 1. Then we decrement register 0, and we use register 0 as a counter, comparing it with 1. So we jump back to here, instruction 5, if register 0 is greater than or equal to 1. And then finally, to signify the end of the loop, we just display the final results of register 1, which would be 55 in decimal and 37 in hexadecimal. So here we are back at the board. These are the instructions that are actually inside of the instruction memory. They're the same as what was displayed on the screen earlier. Right here. That's the last instruction. Now we're actually going to start running this program and seeing if it performs as advertised. So the first instruction performs an AND immediate with 0, so the ALU output should be 0. Yes, and the program counter should point to now the first location instruction memory, 1. The next instruction adds 10 to register 0, so the ALU output should be 10 in decimal, or A in hexadecimal. A. And if I check the program counter, it should now be pointing to the second instruction in memory, 2. Right. Next instruction clears register 1, so ALU output should be 0, 0, and now PC should point to third location in memory, 3. Good. After that, we are going to set register 2 to 1 by first clearing it to 0, 0, PC counter now is at 4, and then adding 1 to it. PC counter is now at 1. I'm sorry, ALU up is 1, the register is 1, and the PC counter is now at 5, which is the first instruction of the loop. The next instruction will be the first instruction of the loop. So the first instruction of the loop is an addition of register 0 to register 1. So the output of the ALU should be A. And it is. And right now the PC should point to location 6, and it does. The next instruction decrements register 0, which is currently at 10, so the output should be 9. And the instruction following is a branching instruction, which uses subtraction to compare. So it's comparing what's in register 0 to what's in register 2, which is currently 1. So the output should be 9 minus 1 is 8. That is what it is. What happens is, if whatever is displayed on the screen is less than 0, then it's going to branch. It's not going to branch. If it is greater than 0, then it will branch, and it will go back to the beginning of the loop. And this is greater than 0. So what we should see is the program counter has decreased. It's pointing back to the beginning of the loop, which is 5. And once I push my manual clock, we should see that the output will be 19 in decimal, which is 13 in hexadecimal. After that, the output of the ALU should be 8, because it's decrementing what's in register 0, which was 9, so it's 8. After that, it's going to be comparing 8 with 1 and seeing if it's greater than or equal to 1. Which it is, so we should see the program counter decrease back to 5 after I push this button, and we do. So that's how it's working. Let's just finish up the loop quickly. And the final result should be 55 in decimal, or 37 in hexadecimal. So right now we're at the last iteration of the loop. Register 0 is currently 0, which is less than 1. What we're going to see is on the next screen, we're going to see something that's less than 0, so we're not going to branch this time. And instead we're going to execute the very last instruction of this program, which just displays the contents of register 1, which accumulated our result of 55 in decimal and 37 in hexadecimal. 37. Thank you very much for watching my demonstration of a single cycle CPU with a read-only instruction memory.